Great, so this is the first FRQ on differential equations dealing with the bird. We started this in class. So for the first part here, they want to know when is the bird gaining weight more quickly, when he weighs 40 grams or 70 grams. And we had started this. This is where we were plugging into that derivative, which represents the weight, the rate that the bird is gaining weight. So when he's 40 grams, if I plug into that derivative, B is 40. I would get 60 divided by 5, which would give us 12, and it would be grams per day. And then if we look at that same equation, evaluated for B is 70, we would get 6 grams per day. So your conclusion is the bird is gaining weight quickly when it weighs 40 grams. So that's the first part. The second part talks about the second derivative. So I'm just going to clear this and slide this down a little bit. So the second derivative is the first part for B, and then they want us to talk about this graph here. So back up here in the original equation, the original first derivative, you can leave it the way it is. If you'd prefer to get rid of the parentheses there and make it 20 minus 1/5 B, you could do that. So the second derivative, d2b over dt squared, would be derivative of 20 would be 0. Derivative of negative 1/5 b would be negative 1/5. But you just took the derivative of something that was in time, so we'll have db over dt with it. And db over dt was that 20 minus 1/5 b. And negative 1/5 times 20 would be negative 4. And negative 1/5 times negative 1/5 b would be plus 1/25 b. So that's our second derivative. And then they ask, explain why this graph can't be the graph of that. So using that second derivative that we just came up with, if I set that second derivative equal to 0, I would come up with possible inflection points. It could also tell me about the second derivative, tells me about the concavity of the graph. So I get a value of 100. If it was first derivative, that would be a critical value. For second derivative, this is a possible point of inflection. So if I use that value to test some values in that second derivative, now this represents, the x-axis represents the bird's weight on my little graph here. So the bird's weight when time was 0 was 20, so I can't pick a value smaller than that. And then the bird would continue to gain weight there. So if I plug into my second derivative a value that's between the 20 grams that it weighed when time was 0 up to 100, like 50, and then pick a value bigger than that, I'm going to pick 200. Because I need to plug these into my second derivative equation, which was, right here. So 50 is going to be an easier number to plug in. 50 divided by 25 would give me 2. Negative 4 plus 2 gives me a negative value. If I plug in 200, 200 divided by 25 would give me 8. Negative 4 plus 8 gives me a positive value. So you should have an inflection point at 100, so we could talk about that there is no inflection point there. The graph is concave down. That's one reason why it doesn't work. The other thing that you could say is between B is 20 and B is 100. So B is 20 and B is 100. That's this side here. My graph should be concave, negative would be concave down. And if you look at this graph here it's concave up, and this part it's concave down. So it's not changing concavity in the right spot there. So you can use either one of those as your explanation. Graph is not concave down for all values. So for the values for B between 20 and 100, you don't have, it's not concave down the entire time. So that's part B, and then part C is the separation of variables, and this is a part that's on all of the differential equation problems. This is always one of the pieces. It's usually the last piece. So if we look at this, they said use separation of variables to come up with the particular solution at that point. P of 0 is 20. So that original equation then, just write it down for you here. That was the dB over dt. Is the 1/5 100 minus b. So we want to come up with the original equation b. So I'm going to need to integrate this. So you want to separate the variables. I have this dB in the top over here on the left-hand side. So let's get all of the b's on the left. So I'd have to divide both sides by that 100b. And I need to get rid of the dt that's in the bottom on the left-hand side. Let's multiply both sides by dt. So now you have b's on the left, you have t's on the right, so now you can integrate this. And usually, these problems are usually worth about 5 points. This piece right here, just separating the variables, is worth 1 point. So integrate both sides. On the right-hand side, if you integrate 1/5 with respect to time, you get 1/5 t. Plus our constant needs to go on either one of these sides here. And then dB over 100 minus b, this is going to require a u substitution. So if I let u equal the bottom, the derivative for that is going to give me -1 dB dt, or dB. And I don't need the negative, we'll put it on the other side and make that negative dB. So my left-hand side then is going to be negative du over u, and du over u integrates to natural log of my u, which was 100 minus b. All right, so now we need to simplify this thing here. I don't like the negative on the left-hand side. If I multiply both sides by a -1, remember that constant just stays plus c. We haven't evaluated that, the value for the constant yet. Let's put the negative on the right-hand side. And now you can leave it this way and plug in your given point when t is 0, b is 20. Or if you want, you could solve for b. I would probably solve for b at this point. So to get rid of the log, we'd have to write this in exponential form. It would be base would be e. Logarithms equal exponents. So my exponent would be -1/5 t plus c. And that would equal this inside part of 100 minus b. And you could put this plus c that's in the numerator. Remember, that can come out in front as the coefficient, because if you're multiplying the same base, you would add the exponents. If you're adding the exponents, you could change that to e to the -1/5 t times e to the c. We'll make that a constant out in front. So if you haven't done so yet, now you would plug in your point. So my b value was 20, and my t value was 0. So this on the right-hand side here is e to the 0, which is 1. We get a constant of 80. So if I plug that back into my equation here, right at that point there, 100 minus 100 minus b equals my c value 80, -1/5 t. And then we'll just get the b by itself. So 100 minus the 80 e to the -1/5 t. All right, so where are those points broken down? Like I said, 5 points for this. It's 1 point for that final answer there, 1 point for coming up with that constant for c, 1 point for, like I said back here, separating the variables, 1 point for integrating and getting that plus c value on the end. That's 4 points, and then the 5th point is in here solving for that, solving for the c value, going through and trying to find that value. So 5 points, sometimes 4 points, but usually 5 points for that one. All right, and then the next problem was the The crap problem. We have a landfill. It's filled with solid waste. When time is 0, you have 1,400 tons of solid waste in this landfill. So they gave us the rate that the landfill is filling up. W is measured in tons, T is measured in years, and then we need to go through and, for the first part, use the tangent line to estimate this. So that's going to be something that's slightly different. So they want us to use the tangent line to the graph W at T equals 0 to approximate the amount of solid waste in the landfill for the end of the first 3 months. And they gave you the hint that you're measuring time in years, so 3 months would be 1/4 of a year. So in the equation of tangent line, I'm going to need a slope. And for a slope, I need the derivative. So they gave me the derivative. And I'm going to evaluate that when T is equal to 1/4. Now, the difference with this one is you don't have a T in your derivative equation there. But I do know when T is 1/4, they said use the value for T is 0 to approximate that. So from the original problem there, they said T is 0, you have 1,400 tons. They want us to plug in 1,400 tons to estimate that value there. So W, when time is 0, is about 1,400. So when it's 1/4, it's going to be a little more than that, but not much more. So this gives us 1,100 divided by 25, which is going to give you 44 for that. All right, so that's going to be our slope. So we can use this to estimate. It's our derivative evaluated at 0, or approximated at 0. So now the equation of the tangent line, you can think what you have for that. It would be y minus your y value. We're not using y, we're using w, equals your slope. And then it's not x, it would be t minus your t value. So if I plug my values in for that, I would have my w minus the 1,400 equals the slope value, which was the 44 we just found, t minus the t value that we used to estimate, which was 0. And you could leave your answer that way. If you solve it, you would have 44t. And then if I put the 1,400 on the right-hand side, it would be plus 1,400, would be the equation. And then finally, they want to know what's w of 1/4. We were estimating this. So 44 times 1/4 plus 1,400, that's going to give us 11 and 1,400, which would be 1,411 tons. So 1,411 tons there for that one. That's pretty hard. I mean, the first derivative part wasn't too bad, but the equation of the tangent line, that was pretty different there. That part was 2 points. It was 1 point for coming up with this derivative and 1 point for this answer. So it wasn't a lot of points for that problem there. For part B, they want the second derivative. So, that's something that you certainly know how to find. And there's not a whole lot of, deciphering what's going on in the problem for that. All right, so this was my first derivative. If you don't like it that way, you want to distribute that 1/25 through the parentheses, you can. At 300 over 25. If you want to leave it, the way it is, that's fine as well. So second derivative, 1/25 w is going to be, derivative would be 1/25. You took the derivative of something that wasn't a t, so you'll have dw over dt. And the derivative of that 300 over 25, if you simplified it or not, its derivative is 0. And then finally, we can take out that dw over dt and replace it with what it was equal to. So it was 1/25 w minus 300. And there's your second derivative. You don't have to do anything else with it. That's fine. And then the second part of it says, determine whether your answer in part A was an underestimate or an overestimate for the amount of solid waste in the landfill. So when T is 1/4, you have, we want to determine what's the concavity, what's the shape of the graph doing. So if the graph is concave up and you estimate it, your tangent line is going to fall below. It's going to be an underestimate. If your curve is concave down, the equation of your tangent line there is going to be above the curve, so it's going to be an overestimate. So really, if we can figure out the concavity, we can figure out whether we had an underestimate or overestimate. And concavity is determined when that second derivative is positive or negative. So if we want to, I would simplify this. I don't like all of these parentheses here. I would probably rewrite this as 1 over 625. And if I distribute that through my parentheses, I would have 300 over 625. Oops, I missed my W. So 300 over 625. And then if you plug in your values, if I set this equal to 0 and find a critical value for this thing here, let's see. Well, I don't even have to work that hard because I already know the value for W. Let me go back here to not simplify. So if I left this as 1/25 W minus 300, if I take out that W and replace it with that value that we came up with in part A, which was 1411, you could do what I was doing, but it's going to make it more complicated. This out in front is 1 over 625. 1411 minus 300 is 1111. I just need to know, is that positive or negative? That's a positive value. Since it's positive, that means our curve is concave up. At, let's see, it's W. So W would be concave up since that derivative is positive. So what's our value? Is an underestimate. All right, so just determining that concavity there makes it an underestimate. All right, and then part C is the big part that's worth 5 points. So part C, there's your first derivative. The condition is when time is 0, you have 1400 for that outcome. So we want the original equation. So again, we got to separate the variables. So W's on the left side, T on the right-hand side. So that's 1 point just separating the variables there. Integrate both sides. Oh, I missed my dt here. Dt. Integrate the left-hand side. You can do the u substitution if you want, or you might just recognize that it's going to be natural log of W minus 300. You need to write out u substitution and do it. You'll have d over u, and you'll end up with that. And this is 1/25 t plus our constant. Then again, we put an exponential form. E to this 1/25 t plus c equals that inside part of W minus 300. That c can come out in front as the coefficient. And you can solve for W, or at this point, if you want to plug in the point. So that's going to give us W, which was 1400 minus 300 equals c e to the 1/25 times 0. So 1100 is your c value. So our equation then would be W minus 300 equals the c value, 1100 e to the 1/25 t, and then get W by itself. You can make a W or W of t if you want to put the variable in there. And 300 could go first or last, it doesn't matter. All right, so again, 5 points for that one. Separating the variables, integrating the plus c value in there, coming up with the c-value, and then the final answer for that piece.